Okay. So first of all, we talk about question 1. Which one of the following points cannot be the intersections for the original function and the inverse function? We can see it's not writing as f equals to y equals to f inverse x. Instead, they write x equals to fy. You know that they change the position of x and y, swap position of x and y. So that is an inverse function. It's equivalent to say y equals to f inverse x. Okay, so which point cannot be the intersection? We know that intersections for those two functions must have the property that x equals to y. So now you can see which coordinates do not have x equals to y, which is D. Okay, so this is an easy multiple choice. And I want to talk about number 2. So if A and B are real constant, for what relationship, okay, I'm asking for what relationship between A and B will the function, okay, we have a function like that, have inverse function. Okay, to have inverse function, fx must be one-to-one function. Okay, I think I forgot to mention that last lesson. So fx must be one-to-one function. In order to find an inverse, this function first needs to be a one-to-one function. Think of if it's a one-to-many function. If it's a many-to-one function, then we find the inverse. That would become a one-to-many function, which is not a function anymore. It becomes a relation. So we cannot say that's an inverse function. It's an inverse relation. So in order to get both function to become both relation to become functions, we need a one-to-one function at beginning. So we need a one-to-one function. So now we have fx is a quadratic. Okay, fx is a quadratic. So because that's a quadratic, think about it's a many-to-one. Okay, I'm not drawing the y-axis. I'm just drawing the graph like that. Okay, so think about this. We have, if that's the turning point, if we cut this into half, okay, left-hand side will become a one-to-one function, right-hand side will become a one-to-one function. Okay, left-hand side and right-hand side, they can be one-to-one function. So I cannot go beyond the turning point. If I go from the left, I cannot go beyond the turning point. Okay, if I start from the right, I cannot go beyond the turning point as well. So I either start from the left-hand side, stop before the turning point, or I can start after the turning point or equals to the turning point to infinity. Okay, I can start two directions. I can start from the negative infinity until the point or before the point of turning point. Or I can start from the turning point or after the turning point until infinity. That's the two parts which can give me one-to-one function. I cannot have a domain which include the turning point in. If I include my turning point and go beyond the turning point, that will be a many-to-one function. You will have a part like many-to-one functions. So now we think about, okay, the function start from negative infinity. The a value needs to be smaller or equals to the turning point. Is that correct? Okay, I cannot go beyond the turning point, so the point needs to be stopped before or just stop at the turning point. Okay, the a value cannot be here. If a value is here, I have a many-to-one function. So the a value must be somewhere before this direction. Okay, stop before the turning point, you reach the turning point. So I need to work out what is the turning point. So turning point is x squared plus 2bx plus b squared minus b squared if I'm trying to complete the square. Okay, plus half of the middle value squared and subtract that value squared as well. So that will give you x plus b squared minus b squared. Okay, for the first three, that become x plus b squared and minus b squared. So the turning point is minus b and minus b squared. Okay, minus b and minus b squared. That's the turning point. If that's the turning point, your A value must be smaller or equals to the turning point. Okay, cannot greater than the turning point. So the A value must be smaller or equals to negative B. So the relationship between A and B, just A plus B needs to be smaller or equals to 0. Or you can just say A needs to be smaller or equals to negative B. It doesn't matter, so both ways correct. Okay, so that's question 2. So question 2 is not asking for a specific value. Not asking for a specific value, it's asking a relationship. If it's a relationship, you talk about, okay, how large or how small, or the add up should be smaller than 0, the add up should be greater than 0. That's the talk about the relationship between A and B. If I'm asking what is the largest value for A, so largest value for A is A equals to negative B. Okay, so the largest point it can reach is on the turning point. So if I'm asking about the largest value for A, that will be A is the turning point. Okay, A is the turning point. Okay, that's question 2. There are some exercise here. I just want to do, which one? Let me see which one. I want to do question E with you. Okay, for question E, I have R minus, and then I have fx equals to x squared minus 4. So, number 1, I'll talk about the domain of f. The domain of f will be negative infinity to 0, but not including 0. So the R minus is not including 0. Same as z minus z plus is not including 0. And number 2, what is the range for f? Okay, so if we can sketch x squared minus 4, the graph will look like this. That is the point negative 2, that's the point 2, that's the point negative 4. And I'm taking negative infinity to 0. That will be the left-hand side of the graph, not including this point. That's an open circle. So the range of f will be negative 4 to infinity. The lowest value is negative 4, but not including negative 4 because you cannot take x equals to 0 and to infinity. And number 3, change the position of x and y. So x equals to y squared minus 4. Y squared equals to x plus 4. Y will equals to plus minus root x plus 4. Okay, so again, I don't know whether I should take plus or I should take minus. So I'll leave it here first. And number 5, talk about the domain of f inverse, which is the range of f is negative 4 to infinity. And number 6, I'll talk about the range of f inverse, which is negative infinity to 0. And we can see what we need. Okay, so I'm looking for the range of f inverse. Okay, the range of f inverse is negative infinity to 0. I need all the negative values. Okay, they are all negative values. There's no positive values. My range for the function needs to be negative. If the range needs to be negative, the square root is positive. I need the range is negative. I need to have the negative sign in front. So y should equals to negative square root x plus 4, not positive. Okay, does that make sense? I need a range of negative infinity to 0 is all the negative values. And I want this y to be negative. How this y can be negative? You need a negative sign in front of the square root because the square root will give you a positive value. And the positive value, put a negative sign, that will give you the negative value. So you should take the minus sign instead of the plus sign for this question. Okay, have a think about this. Like the 2 examples we show on the class is all positive values. We take the plus sign. Now we take the minus sign because the range is negative. That's why we take the negative sign. So I will write my f inverse is the domain -4 to infinity, mapping to r, comma, f inverse x equals to -√x plus 4. Okay, so that's for this question. And I'm going to go back to have a look at question 1. Okay, I'm going to go back to have a look at question 1. Question 1, if you have the lesson on Monday, you should know that linear and linear is a hyperbola graph. Okay, it's a hyperbola graph. And how we can make that type of graph. Okay, for question 1, how we can make the standard form for hyperbola graph. We'll make that looks the same as the bottom. Okay, I want to look, the numerator looks the same as the denominator. But I actually have -2, but I plus 2 here. It's not good, so I need to subtract 4 from that as well. To make, so the numerator is still x minus 2, but I have one part which looks exactly the same as the denominator. And now I can separate that. -4 and x plus 2. That gives me -4, x plus 2, and plus 1 at the back. Okay, so now you can see that's a hyperbola function, and we can talk about the domain for f. So the domain for f is r except -2, is r except the value that can make your denominator become 0. So if x equals to -2, the denominator will be 0, so you don't want 0. You need r except -2. Number 2, what is the range for f? Okay, the range for f, the range cannot take the constant, so which is the 1. Okay, so I don't need the graph, I can directly see what is the domain and range. Number 3, I change the position of x and y. So x equals to -4, y plus 2 plus 1. Do not substitute in this one. Okay, do not substitute in this one because you have two y values if you substitute in that one. It increases your difficulty level of doing this question. If you can substitute the one we already simplified, you only have one y and it's easy to solve. Okay, just choose one which can make you easier like to solve this equation. And number 4, I want to make y to be the subject. So I have x minus 1 equals to -4 y plus 2. And I can times y minus 2 on both sides of this equation. And I can divide x minus 1 to the other side. And y equals to -4 over x minus 1, subtract 2. Number 5, what is the domain for f inverse, which is the range for f is r except 1. And what is the range for f inverse, which is domain of f, which is r except -2. If in the function notation, I'll say that f inverse domain is r except 1, mapping to r, f inverse x equals to -4 over x minus 1, subtract by 2. Okay, so part B, you will wait until we finish today's lesson. You can come back to do part B. Okay, it's a power function. So wait until we finish today and you come back to do this one. What you can see from question 1, you know if it's a hyperbola function, the inverse will be a hyperbola function as well. Okay, that's what you can see from the result. If it's a hyperbola function, the inverse will be a hyperbola function as well. Okay, if the function is a quadratic, your inverse function will become a square root. If it's a cubic function, your inverse function will become a cube root. If it's a log function, inverse will become exponential function. Okay, they're all pairs. So you can check your values, you can check your answers. if you have a square root function and then you finally work out okay, if you have a square quadratic function and you have another quadratic function as your inverse, you know you make some mistake. There should be a square root. Okay, so you just compare your values, compare your answers. They should all match. Okay, they should all match. Okay, so I have a lot of examples put in here, and you can see we have sine function as well, and we have number 3. You need your CAS. For this one, you can use your CAS to help you. And that can be a CAS question. Number 3 on page 29. Okay, I'm not going to do more examples about inverse function. You learned that in year 11, and we are not really having a lot of things new here. Maybe one thing. Let's go back to question 1, what we have done in question 1. Okay, now if I just want to show you one thing. Okay, I want to find point of intersection or intersections between fx and f inverse x. Okay, I want to find point of intersection or intersections between fx and f inverse x. Okay, so you have your fx equals to what we have, minus 4 over x plus 2 plus 1. And we have f inverse x equals to minus 4 x minus 1 minus 2. Okay, that's the two functions. And you can see if we want to solve them simultaneously, that will be really difficult. Okay, it will be really difficult. We have two fractions and we have two constants. I don't like to solve by this way. So what we can solve is solve simultaneously by y equals to x and choose any function you looks good. Okay, I'll choose the first one. Okay, why I choose the first one? There's a reason why I choose the first one. Okay, think about if in a test you make mistake in part 1 and you give a wrong answer for the inverse function. And now the second question is asking you for the intersections between the graph. Which equation you should use? You should use the original one for sure. Because if you use the original one and you use y equals to x, so solve that simultaneously, you definitely have the correct answer for the point of intersection. Even though you make mistakes to give a wrong inverse function, you still get the mark in part 2. Okay, that's how you can get marks. Okay, if you use your answer and your answer is wrong, you may get consequential or you may not get consequential. It totally depends on how they mark the paper. Okay, so try to use and also sometimes they may not give you consequential for this type because you can find the correct answer by using the original function. So your answer doesn't really make like any changes. So use the most correct ones, okay, with like really confident ones, which is the original one. So I will use those two to solve for points of intersections. And now I will have x equals to that, and I can minus the 1 to the side and get rid of the denominator equals to minus 4. And I have x squared minus x plus 2x, which x squared plus x minus 2 plus 4. We have a minus 2 and we have a plus 4 moving from that side. We have x squared plus x plus 2 equals to 0. Okay, can you see we have no intersections between those two graphs? Okay, the discriminant equals to 1 squared minus 4 times 1 times 2. That's smaller than 0, and we do not need to work out further from there. So there's no points of intersections. But what I want to show here is how we can find point of intersections and what equations we should use to find point of intersections. Okay. Okay. Now let's move on to power functions. Page 30. Okay, so I'll go a little bit revision here. If you can remember, that's from chapter 6 from year 11 book. Okay, I'm doing a little bit revision here. So we have power functions. Power function, we only talk about power function last year on Z class. We only have integer values for the power. So we have all the even powers and we have all the odd powers. But like it's x to the power of 2, x to the power of 4, x to the power of 6, and x to the power of 3, x to the power of 5, x to the power of 7. We have those graphs. And now I want to show you what the graph looks like. So if we have x to the power of n, where n is an odd number, So what the graph will look like, I will show three graphs. We'll show x to the power of 3, x to the power of 5, and x to the power of 7. Okay, so what the graph will look like. Let's sketch x to the power of 3 first. Okay, that's x to the power of 3. Okay, if we have x to the power of 5, where will they intersect? If we have x to the power of 3 and we have x to the power of 5, where's the point of intersections? 0, 0 is definitely 1. How about other points? If we have x to the power of 5 equals to x to the power of 3, so what values we can solve out? 1, 1, 1, and another point, -1 and -1. Okay, we have 3 points of intersections. So we know that we will have 0, 0 as point of intersection, 1, 1 as point of intersection, as -1 and -1 as point of intersections. And tell me, which graph will be higher? Like, which graph will have a larger values? X to the power of 3 or x to the power of 5? X to the power of 5. Okay, after the point 1, you definitely have a graph higher than the x to the power of 3. But think about, we have points of intersection at 0, 0. We have another point of intersection as 1, 1. And you know after 1, the graph will be higher. So in between 0 and 1, how the graph can like work? Okay, you cannot have higher and another higher and you still have intersections. So we need to have our graph slower in the point here and go up here. So the graph needs to be lower here and then higher here. That should be the point of intersection. Okay, that should be the point of intersection. In between 0 and 1, the graph should be lower. And then after the point 1, x to the power of 5 should be higher. And if you have x to the power of 7, it will be the same reason. That will be even lower at this point and even higher at this point. So this green one will be x to the power of 7. The graph is a little bit like not very good looking, but like that's the idea how the graph will work. So in between 0 and 1, the higher the power, the lower the graph. After the point 1, the higher the power, the higher the graph. I know you have like really bad graphs, but like it's okay. I'm not going to ask you to sketch 3 graphs on the same set of x-axis. So you just need to know where the graph should go. Okay, so same for the even power. So for the even power, okay, let's say we have x to the power of 2. Okay, that's a perfect quadratic. That's x to the power of 2. And I know I will have point of intersection at 0, 0. I will have point of intersection at 1, 1, and negative 1 and 1. Okay, if you try to think about 1 to any even power will give you 1, negative 1 to any even power will give you 1. And same thing, if we have x to the power 4, that should be higher than the graph after 1 and negative 1 and lower in between negative 1 and 1. So the graph will be look like this for x to the power 4. That's for x to the power 6. Okay, now we use this idea to think about we can have any power. We can have fraction powers, we can have proper fraction powers, we can have improper fraction powers, we can have power with odd numerator and even denominator, we can have even denominator or even numerator or denominator, or we can have odd and odd denominator. So I classify the power into 3 different forms. Okay, so let's say we have x to the power of n. I give you a chart to think about. Let's think about we have x to the power of n, where n belongs to rational numbers. Okay, anything can be written in the fraction form. Okay, now my power can be classified as 3 types. Okay, odd on odd, and even on odd. Okay, can I have even on even power? Even on even, is that worked? Can I have even on even? So what is an even number? Like contain 2, right? It's a like 2 times something. It contain a factor of 2. Think we have even power on even. We all contain 2. We can divide that by 2. If it's still even on even, we can divide by another 2 until it reach 1 even, 1 odd, or 2 odd, right? Like we can keep reducing or keep factorize or keep like canceling the 2's until it reach 1 of this form. So think about 6 and 6 over 8. We can simplify to 3 over 4. So 3 over 4 will become odd on even. Okay, so it can reduce back to the 3 form here. Okay, now I have this type of equation. Let's look at the first row. Okay, we can look first and second together. Okay, we can look first row and second row together. Okay, what's the important idea for power functions? We need to think about 2 things. Okay, the first thing is which quadrant I should have graph. Okay, which quadrant I should have graph. And the second is n greater than 1 or n smaller than 1. Okay, which is like the stiffness, decide the stiffness. It's the STEP. It's decide the stiffness of your graph. Okay, it's whether increasing very fast or increasing like very flat. Okay, so we look at 2 things. Okay, so for the first thing, we need to know that let's write our question in x to the power of p over q form. Let's write that it's a fraction, right? It's a rational number, it's p over q. How about what's p over q represent? It represents x to the power of p and take the q's root. Okay, that's what it means for fraction power. It's x to the power of p, or like, and then you root for q's root for the x. Okay, now think about, you have p is an odd number. Okay, P is an odd number. And Q is an even number. Q is an even number. Let's take an example. Take an example as x to the power of 1 over 2. X to the power of 1 over 2. That's a square root. Okay, the simplest one is the square root function. So, or you can say x to the power of 3 over 2. Okay, or 4. Let's say x to the power of 3 over 4. Let's talk about the numerator is smaller than the denominator. Okay, for this type of graph, which quadrant I will have a graph? Which quadrant I will have graph? First of all, if x is positive, after you cube it, it's still positive. And then you take an even root, you still have a positive number. So if you have positive x, you still have positive y. So the graph must be in the first quadrant for sure. So I will do this. So in the first quadrant, it's satisfied. For the second, think about if x take negative number. After you cube it, it's still a negative number. And now you want to false root of a negative number. Is that possible? It's not possible. So I cannot have x equals to negative. Okay? My graph will only be in the first quadrant. That's how you think about this. Okay? Think about positive x and what y value I will have. Think about negative x and what y value I will have. Okay, you can check examples. You can check any examples. They will give you the same result. Okay, maybe it's not very making sense. Let's think about the next one. Next one is odd on odd. Let's say x to the power of 3 and to the power of, take the fifth root. If x is positive, I cube it, it's still positive, right? And I fifth root of it is still positive. Positive x and positive y. Okay, I have graph in the first quadrant. If x is negative, I cube it, it's still negative. I fourth root of it, it's still negative. I have negative x and negative y, so I have graph in the third quadrant. Okay, I will have graph in those two parts. Now think about even on odd. X to the power 4 take the root of 3. Okay, cube root. X to the power 4 take root 3. When x is positive, x to the power 4 is positive. Take the cube root, is still positive. Okay, first quadrant is fine. If x is negative, you root that. You 12 4. Okay, to the power 4 it will become a positive number. X to the power 4 will become a positive number, and then you try to cube root that. That's still a positive number. So you take negative x, that still give you a positive value. So you will have in the second quadrant. You take negative x, you will have positive y. So you have graph in both first and second quadrant. Is that making sense? That's how you make sure which quadrants you will have graph. And what you can see from those three types, you will always have graph in the first quadrant, and you just need to worry about whether I'll have a graph in the second quadrant or third quadrant or no, just no graph for negative x values. So just need to test about your x negative, okay, negative values for x. And think about whether it should be in the second or in the third or just no for x negative. Okay, that's for the quadrant. And the second thing you need to talk about is the stiffness of the graph. So let's just take off that. The stiffness. Okay, now I tell you, if your power is a number smaller than 1, you will have a really slow growth graph. It's more flat. But if you have an n greater than 1, look at the graph. They are in the exactly same quadrant. But you will have something grow really fast, really steep graph. Can you see they exactly in the same quadrant? What's different is only the stiffness of the graph. If n is greater than 1, you will have a graph grows really fast. You will have n small, okay, for say the smaller than 1, I would say n is in between 0 and 1, not really smaller than 0. So in between 0 and 1, you will have a graph that grows really slow. Okay, but it still grows, still increase graph, but grows really slow, more flat. Okay, so that is what you have for positive power. Okay, they're all positive. So for those powers, they are positive powers. Okay, the next thing I will give you some examples, like what's the graph will look like. Okay, for this one is x to the power of a half. For this one is x to the power of a third. And for this one, we don't really know what type of graph should that be, so the easiest one will be 2 over 3. And for the bottom one, we have x to the power of 3 on 2. For this one is x to the power of 3 on 1. Okay, that's x to the power of 3. So if it's a whole number, it's just 3 on 1, 3 on 1. So think about that's a cubic function. And for this one is x to the power of 2 on 1. Okay, x to the power of 2 on 1. Okay, for the first two and last two, we know like what the graph will exactly looks like. You will think about those examples. Okay. The next one, which is a little bit hard to think about, but let's try. Okay, we still have x to the power of negative n. N is still p on q. Let's say that's still x to the power of negative p on q. So what's that equivalent to? That's equivalent to 1 over x to the power of p on q. And that is equivalent to 1 over x to the power of p at q's root. Okay, so what you can see compared to the last one and the first one, you just 1 over that. It's like the reciprocal function. You 1 over of that function, right? Okay, so now let's go back. In the negative part, we don't really care about p over q is greater than 1 or smaller than 1. Okay, we only have one type of graph for the negative values. Okay, so we have 1 divided by that x to the power of p over q. Let's go back to x to the power of p over q. So that is a graph x to the power of p over q. Okay, that's a graph x to the power of p over q. I want to 1 divide by the y value. I want to look at 1 divide by the y value. So if I want to divide by that, think about when x equals to 0. X cannot be 0. Okay, x cannot be 0 because you have a y value equals to 0. So that's not good. So at this point, I will have an asymptote. Here. Because x cannot take 0. Because 1 over 0 is undefined. So at that point, you have asymptotes. Think about the behavior that x become really large. This x to the power of p on q become really large, right? Become infinity. Okay, 1 divided by infinity, what's that approaching to? 1 divided by a really large value, what's that? 1 divided by 10,000, 1 million, what that should be? About to 0, okay? Approaching to 0. The larger the x, the smaller the y value is more approaching to 0. And tell me when x is really small and this y value is also really small, 1 divided by a really small number, what that should be? Approaching to infinity. 1 divided by 0.000001, that approaching to infinity. So you will have a horizontal asymptote here as well because it's approaching to 0 in the end. So the inverse, the reciprocal graph is just look like this. Okay, it's the other way. You draw the x to the power of p over q first and you think about 1 divided by that function, what will happen? 1 divided by a really small value, that will really approaching to positive infinity. If you divide by a really large y value, that will really approaching to 0. So your graph will look like the blue one. Okay, it will look like the blue one. So I will take off this to avoid confusion. So let's come back. See, we have this graph. Okay, we have this graph. You need to show asymptotes. I cannot draw asymptotes for my graph, but like you need to show asymptotes here. Okay, when you sketch your own graph, you need to show 2 asymptotes. The vertical one is x equals to 0, and the horizontal one is y equals to 0. And now you have that's What is that? That is odd uneven. This is odd uneven. And now you will have odd on odd. Okay, let's go back to the odd on odd graph. Okay, this is my odd on odd graph. Okay, my odd on odd looks like this. Now the same thing happened. I will have asymptotes here because y value equals to 0 at this point. I will always have horizontal asymptotes. And because the graph is approaching to 0 to this side, I will have this graph. And this side will have this graph. Okay, same reason. Divide by a really small y value, you have a really large y value. If you divide by a large y value, you will have a value approaching to 0. Okay, so we'll have those two parts of the graph. If you think about what is this? This is x to the power of negative 1 on 1. Okay, x to the power of negative 1 on 1, which is the hyperbola graph. Okay, it looks exactly the same as a hyperbola graph. It will be the first and third quadrant, but with hyperbola graphs. Okay, next one is a truncus graph. This will be x to the power of negative 2 on 1, which is even on odd. Okay, let's look at this, the above graph. I want to use 1 divided by this graph. This is a quadratic. Okay, same reason I will have vertical asymptotes because y equals to 0 here, and I have horizontal y, always have horizontal and vertical y. And now your graph will look like this because you divide by positive value, really positive value, you get a value approaching to 0. You divide to the value really closing to 0, you have a really large value. Okay, that's how you create your graph. So still the same thing, you will make sure which quadrant you graph in, and you find the inverse reciprocal function of that 1 divided by that value. If you can't see, you can find the original graph first, and then you try to see, okay, at y equals to 0, I should have a vertical asymptote. I should have a horizontal asymptote at 0. And then I should find inverted my graph. When it's approaching to 0, our really y value needs to approaching to infinity. And if I have original y value really big, I should have a value approaching to 0. That's how your graph looks like. Okay, I don't think I have time to do examples here, but I want you to finish the following example. If you can do it, finish the example on page 32. Okay, page 32. Okay, just use the idea we had for the previous page and try to sketch the graph.